For what feels like forever, the mantra in AI has been go big or go home, right? Bigger models, more data, giant supercomputers. But what if we've been chasing the wrong thing? What if the real secret to making AI smarter isn't just about raw power, but about, well, teaching it to think better? We're going to dive into that idea right now.
So this is the million-dollar question, isn't it? How do we get these AI models to be genuinely smarter, not just bigger? I mean, scaling up has gotten us pretty far, for sure, but we're starting to hit a wall where making models twice as big doesn't make them twice as smart. The new game is all about efficiency. It's about taking the power we already have and using it in a much more intelligent way. All right, here's the game plan. We'll start with why we need to focus on smarter, not bigger. Then we'll look at how AI even finds an answer in the first place and a major flaw in how it's been doing that. After that, we'll get to the main event, a cool new strategy called Rollout Roulette. And stick around because the results are seriously mind-blowing.
Okay, first up, smarter, not just bigger. This is really about a fundamental shift in where we're focusing our efforts in AI.
So let's break this down. For a long time, all the hype was around training compute. Think of this like a student cramming for years and years, just absorbing tons of books. That's how we build these models. But there's this other super important part called inference compute. That's like the final exam, the moment the AI has to use all that knowledge to answer one single question. And that's where the new opportunity is. What if, instead of just blurting out the first answer that comes to mind, the AI could actually pause and, think about the problem for a bit longer? The first idea of how to do this was pretty basic. It was kind of just brute force. There's this great paper that called it large language monkeys. You get the reference, right? 1 million monkeys on 1 million typewriters will eventually write Shakespeare. The idea here is the same. You just ask the model the same question over and over and over, and you just hope that one of the answers it spits out happens to be the right one. I mean, it can work, but it's not exactly smart, is it?
Right, so obviously we can do better than just asking 1 million times. The next step for researchers was to try and be more strategic. Instead of just taking random shots in the dark, they wanted to create a more guided, step-by-step search for the best answer.
And a really popular way to do this is something called beam search. Okay, picture this. You're in a maze. Instead of just picking one path, you start exploring, say, 3 different paths at once. At every fork in the road, you've got this little guide with you. In the AI world, they call this a PRM, or process reward model. And it tells you, this path looks way more promising than the others. So what do? You completely abandon the paths that look like dead ends and put all your focus on the top scoring ones. You just keep doing that over and over. Sounds super logical, right? Well, it turns out this has a massive, fatal flaw.
And this is where it all goes wrong. That super logical, step-by-step approach, it can fail, and fail badly, all because of one little problem.
See, the problem is your guide. That PRM we talked about, it's not perfect. It's just making its best guess. The paper calls it an imperfect approximation of true correctness, which is a fancy way of saying it can be wrong. And here's the kicker. In a system like beam search, if that guide makes one bad call early on and says, nah, ignore that path is gone, forever. You can't go back. It's been pruned away, and you might have just thrown out the one and only correct answer.
This is so important to get. I love this analogy. Think of beam search as a super determined but very single-minded mountain climber. Their only rule is always take the steepest path up. Sounds good, right? But what if that steepest path leads to a little false summit, just a small peak? The climber gets to the top, thinks they've won, but they're stuck. Meanwhile, the real summit, the highest point on the mountain, is right over there, but they can't get to it because they can never go back and try a different path. They made one wrong turn, and now the real prize is impossible to reach.
Okay, so that brings us to the hero of our story today, Rollout Roulette. This is a completely different way of thinking. Instead of being afraid of making a mistake, it actually embraces the uncertainty. So the magic behind Rollout Roulette is this technique called particle filtering. Now, forget that single-minded climber. Instead, I want you to picture a whole team of hikers. They all start at the bottom of the mountain together, but they spread out to explore a bunch of different paths at the same time. Periodically, they radio back to each other, sharing notes. Hey, this path over here looks really promising. So more hikers will go check out that promising path. But, and this is the absolute key, they don't abandon the other trails. They always keep a few hikers on those weird, less traveled paths, just in case one of them turns out to be a secret shortcut to the top. No possibility is ever completely thrown away.
And the name, Rollout Roulette, is just perfect. Think about it. That old deterministic search, beam search, that's like walking up to a roulette table and putting all of your chips on a single number, black 17. High risk, high reward. It's all or nothing. But Rollout Roulette is way smarter. It's like spreading your chips out, putting little bets on a bunch of different numbers. And here's the cool part. As the ball is spinning and starts to slow down, you're allowed to move some of your chips to the section where it's more likely to land. But you always leave a few chips on those long shots because, hey, you never know, right?
So what does this actually look like inside the computer? It's this beautiful three-step loop. First, extend. Every hiker takes one more step down their path. Simple. Second, reweight. The guide model looks at where everyone is and gives a new score to each path. The promising trails get a boost in their score. And third, and this is the secret sauce, resample. The team of hikers gets redistributed. The paths with high scores get more hikers, maybe even cloned hikers, but a few are always assigned to stick with the low-scoring, long-shot trails. It's this constant dance between exploring new options and exploiting the ones that look good.
Okay, that all sounds great in theory, but does it actually work in the real world? This is the best part. The results are, well, they're pretty incredible.
Okay, just look at these numbers. They took a set of really hard math problems from a competition. The massive, state-of-the-art GPT-4o. It solved 4 of them. Now, they took this tiny little model, Quinn25, which on its own could only solve one problem. But then they gave that tiny model this new, smarter way of thinking, the particle filtering method. And guess what? It solved 6 of the problems. Let that sink in. A tiny model with a better thinking process beat a model hundreds of times its size. That's insane.
And it's not just a one-off. What the researchers found is that this method is way more efficient. It has a scaling rate that's 4 to 16 times better than the old deterministic methods. What that means is, for every extra bit of computing power you give it to think, you get a much bigger improvement in the quality of the answer. You're just getting so much more bang for your buck.
And get this. This is my favorite stat from the paper. That tiny 1.5 billion parameter model surpassed GPT-4o's score with a budget of just 4 rollouts. That means it only needed to let its team of hikers take 4 steps before it found a better answer than one of the biggest models in the world. Just 4. The efficiency is just off the charts.
And it doesn't stop there. They took a slightly bigger model, a 7B1, which is still a baby compared to the giants out there, and it was able to match the performance of OpenAI's O1 model. Now, for those who don't know, O1 is this legendary, almost mythical model that's supposedly a genius at reasoning. And this little 7B model matched it with just 32 thinking steps. It's just wow.
So what's the big takeaway from all this? It's pretty simple and it's pretty profound. A better thinking process can be way more valuable than just raw size. We have actual proof now that changing how a model thinks, moving from that rigid, single-minded approach to this flexible, keep your options open strategy, unlocks a staggering amount of performance, even in much smaller, cheaper models. And that just makes you wonder, right? If we can get this big of a leap just by improving one part of the thinking process, the search, what else are we missing? What other fundamental parts of reasoning can we upgrade? If making AI think smarter is the new way to scale, then honestly, the next chapter of AI is going to be way more interesting than just watching the models get bigger.